Welcome to Chapter 9, Gases. We're going to be working on Think Aloud Paired Problem Solving, which is a strategy that we use to help us make sense of complex problems. Sometimes hearing someone else's process can help you make sense of how you yourself would solve a problem. We asked you to do some brainstorming around what you already know about gases, temperature, volume, moles, pressure. This is a great opportunity for you to reflect on your prior knowledge and to also do some brainstorming around what you might want to know. Prior knowledge can include what you read in the chemistry textbook, what you already know from a previous class, or maybe your own personal experience. Our goal is that by the end of Chapter 9, you'll be able to fill in this Learn column with some very specific content knowledge and skills, as well as strategies that you've picked up along the way. I had a request from students for examples of marine scientists who in our scientist spotlights. And so I wanted to introduce you to Carl Brashear. He's a Master Chief Petty Officer. He's unique in several ways. The first way is that he was one of the first African Americans to become a U.S. Navy master diver. But I think what is even more impressive is that he suffered a significant amputation and then went on to requalify as a master diver. Divers are incredible scientists because they have to make sense of the gas laws that we're going to be learning about in order to stay safe and be able to continue diving. Carl Brashear was both a salvage and a demolition recovery expert, and because of his significant record, both in service, but also just as a role model and a leader, after his death, the Carl Brashear Foundation endeavors to continue to inform the community at large about his legacy. When we think about science practices, obviously we're going to be asking questions and defining problems today, but we're also going to be analyzing and interpreting data. That's really the focus where we're going to land today. If we think about our learning outcomes for Chapter 9, we're going to be focusing on converting between units of atmosphere, millimeters, mercury, and torr. We're going to relate pressure, volume, number of moles, and the temperature of a gas. And we're going to use the ideal gas law, PV equals nRT, to find missing properties or variables when we're given the other three. And finally, we're going to think about, on Wednesday, how to solve for the molar mass of a gas or the density, and to incorporate masses and densities into PV equals nRT calculations. But today we're going to do some serious work focused on converting Celsius to Kelvin. One of the most important big ideas associated with this chapter is an equation. It's called the ideal gas law equation. It's PV equals nRT. And it's important that we know what each of those letters stand for. This is, if you think about it, the symbology piece of the chemist's triangle. So in this case, we're representing individual variables like pressure and volume, as well as moles and temperature, using letters. And then in addition, we're going to use something called an ideal gas constant. And you're going to notice that there's a column with a specific value, as well as a column with specific units. We want to make sure that we're using the right value and the right units in our calculation. This is critical because using the gas constant is what allows us to actually cancel the other units in our equation so that we can solve for our unknown. I want to introduce you to the idea of pressure. So pressure is force divided by area, or F over A. We typically think of pressure in atmospheres for our purposes, but there are other units like millimeters of mercury, or torr, or pascals, or kilopascals. So when we think about pressure, probably one of the ways in which you've heard about pressure is, say, for example, pressure at high altitudes. That's very low. That's actually why certain types of pilots and folks who climb Everest might actually have to use supplemental oxygen because the pressure of oxygen is so low. There's less oxygen available at a high altitude. But you're also probably familiar with the high pressure at low altitude. So when you're in the ocean, pressure increases. That's actually part of the reason why we have to be really careful when we're on submarines or, say, for example, diving. So in class, we developed the claim evidence reasoning statement For Y at high altitude, there is low pressure. So if our claim was at high altitude, atmospheric pressure is lower than at sea level, what would our evidence be? So the evidence would be that water boils at lower temperature and air density is lower than at sea level. So what is our reasoning then? Well, reasoning would be that the atmospheric pressure pushing down on water in a pot decreases at high altitude, which is what allows the water to boil at lower temperatures at higher altitudes. So a lower boiling point means food cooks at lower temperatures. We're going to use a phrase, standard temperature and pressure, and that has very specific meaning. Standard temperature means 0 degrees Celsius or 273.15 degrees Kelvin, and 1 atmosphere, which is the standard pressure. So where the atmospheric pressure is 1 atmosphere and the temperature is 0 degrees Celsius, how many total moles of air are there in 0.5 liters? So at standard temperature and pressure, we can say that 1 mole of gas occupies 22.4 liters. So if we think about how we would solve that problem, we actually can use that as a conversion factor, but only when we're at standard temperature and pressure. The kinetic molecular theory of gases is another part of the chemist's triangle. In this case, we're thinking about a microscopic model. There are several components to this model. The first component is that gases are composed of molecules that are in continuous motion, that they're traveling in straight lines and they're changing direction only when they collide with other molecules or with the walls of a container. The second idea is that the molecules composing the gas are very small or negligibly small compared to the distances between them. The pressure exerted by a gas in a container results from the collisions between the gas molecules and the container walls. And gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic. They don't involve a loss of energy. And then finally, the average kinetic energy of the gas molecules is going to be proportional to the Kelvin temperature of the gas. So what's the big idea here? The big idea is that gas particles are incredibly small when compared to the space between them. They move randomly and rapidly, that they exert negligible attractive forces on each other, and that the average kinetic energy of a gas is going to be proportional to its absolute or Kelvin temperature. So for ideal gases, probably the most important idea here is that we assume that they occupy 0 volume. This is going to come into play when we think about things like gas laws and diving. Now, there are a variety of named gas laws. You don't need to know the names, but we'll think carefully, especially in discussion section, about the relationship between the variables. Say, for example, the relationship between pressure and temperature, or volume and pressure. And eventually, we'll use both the combined gas laws as well as PV equals nRT, the ideal gas law, to be able to make calculations relating these variables. So, for example, you're going to think about in discussion section that volume is inversely proportional to pressure. This symbol is inversely proportional, and it tells us that as volume increases, pressure decreases. We can also see that using this equation. We can look at volume being proportional to temperature, and we can also say that pressure is proportional to temperature. And the combined gas law is something that we'll practice with in order to solve for individual variables. If you want some additional practice thinking about gas laws, how to solve the equations or make sense of individual variables, come check out Science Student Success, or S Cubed, from 11:30 to noon. You can also get additional help in discussion sections. And finally, it would be great if you took 5 minutes to organize your goals, think about your thinking, and reflect on your learning. If you have any questions, please don't hesitate to come and see me. Have a great day. Thanks so much.